The three containers shown below all have the same area at the base and are filled to the same height with water. In which container is the force exerted by the water on the base of the container greatest? So we want to figure out the force exerted by the water on the base of each container. We don't know anything about the mass or how much water is in each of these containers, so we're not going to be able to use something like mg. But we can figure out the pressure. So we know that the pressure is force divided by area. So if we want to figure out the force on the base of any of these containers, we can take the pressure at the base of the container and multiply it by the area of the base of the container. So we know that all three containers have area A at the bottom. So that means that A is the same in all three cases. So now we just need to ask which one has the highest pressure. So this is a fluid statics situation. So we know that the pressure at some point P1 is equal to the pressure at some reference point plus rho GH. So for example, in container A, if this is P0 and P1 is at the bottom of the container, we know that P1 has a pressure that's greater than P0 by rho GH. And because the container is open to the atmosphere, P0 has to be equal to atmospheric pressure. So the only thing that this depends on is the depth. And we also know that the depth in each container is h. And in fluid statics, we know that if we have a horizontal line through a static fluid, the pressure is the same at any point along that line. So the whole container, the pressure across the whole container at the bottom is P1. And P1 is going to be the same in each case because the depth is the same. So that means that P is the same in each case. So if A is the same and P is the same, that means that all the forces must be equal as well. So the force is the same in all three containers. You may have noticed that the bubbles in a glass of champagne are smaller than the bubbles in a bottle of soda. If the pressure of the CO2 inside the bubble is the same in both cases, then the surface tension of the air champagne interface must be lower than, the same as, or higher than the surface tension of the air soda interface. So I'm going to start by drawing a picture. So here's our champagne bubble, and here's our soda bubble, and we're told that it's bigger. We're also told that the pressure inside each bubble is the same. So this P in equals this P in. Assuming that the two bubbles are the same depth in the liquid, P out over here for the champagne should be equal to P out over here for the soda. Now, these aren't really bubbles, these are cavities, because when you go from the inside of the bubble to the outside, you only pass through one interface. You go from carbon dioxide to liquid. So it's a cavity. And we know for a cavity that the pressure difference across the curved interface is equal to 2 gamma over the radius of the cavity. So in both cases, P out and P in are the same. So both bubbles have the same delta P. So delta P on this side is equal to 2 times gamma champagne divided by the radius of the champagne bubble. And over here, delta P is equal to 2 times gamma soda divided by the radius of the soda cavity. So because these two delta P's are the same, these are equal. So this is equal to this. So if we equate those two, the 2's cancel, so we get gamma C over RC equals gamma soda over R soda. So we can rewrite this as gamma C over gamma soda equals RC over R soda. Now, because we know that our champagne is smaller than our soda, this is less than 1. And because this is less than 1, we know that gamma C has to be smaller than gamma S. So the surface tension of the air champagne interface must be lower than the surface tension of the air soda inner. Three forces, each with the same magnitude, are exerted on a door as shown. F1 acts at the middle of the door, right here, and the other two act at the end of the door. If the counterclockwise torques, this way, are positive, which of the following statements correctly orders the torques exerted by the three forces? Okay, so they're telling us to compute the torques about the hinge. So we're going to choose this as our pivot. And we need to find the torque for each one of these three forces. So remember that torque is equal to R, which is a vector that goes from the pivot point to the point where the force is applied. So in the case of F1, this is the vector that goes with F1 cross F. So we also know that we can write the magnitude of the torque as RF sine theta, and you can write this as R times the perpendicular component of F, or the perpendicular component of R relative to F. So that just means that if you want to exert a torque, pushing like this isn't going to do anything. So if this is a real door and you push in this direction, you're not going to turn the door. It's only a Y component of a force that's going to do anything for you. So that's all this says. Okay, so if we want to compute the torque for force 1, so torque 1, so I always ask what's the sign first. So the torque due to F1, so F1 would turn the door this way, and that is a positive torque. So we know this is going to be positive. Now what's its R? So the R is going from the pivot over to halfway across this door. We don't know the length of the door, but that's okay. Let's just call it L over 2, so that the total length of the door is L. And then we need to multiply by F sine theta, or the perpendicular component of F. So when I look at this, I see that R is this way, and F1 is at a 90-degree angle to R. So all of F is already perpendicular to R1. So that means that our F sine theta, or our F perpendicular, is just F1. Okay, so let's look at the torque from F2. So the torque from F2. So first, is it positive or negative? So when I look at this force right here, I notice that if I pushed on the door that way, it would actually spin in this direction. So that direction is opposite the positive torque direction. So this must be exerting a negative torque. Okay, so what's the lever arm? So in this case, we're going all the way from, let's change the color here, all the way from the pivot to the point where the force is applied, which is way out here at the end of the door. So that has a distance L. So our R in this case is L. And now we need the component of F2 that's perpendicular to the lever arm. So let's figure out what that is. So minus L times whatever F we find. So we see that F here is at a 45, F2 is at a 45-degree angle relative to the lever arm. So we need to find the component that's perpendicular. So in this case, F2, you could decompose that into two vectors. There's this one, that's the component parallel to the lever arm, and this one, which was the component perpendicular. So we need to find this height right here. So if I just take this, I can move it over here on this side, and it's a little bit easier to see in that case that it's F sine 45. Now in this case, F sine 45 is the same as F cosine 45, but if it wasn't a 45-degree angle, you would want to make sure to be if it wasn't a 45-degree angle, you'd want to make sure that you got the right trig function. So this should be f2 times the sine of 45 degrees, and that is minus L f2, and the sine of 45 degrees is 1 over root 2. So finally, we need to figure out the torque exerted by F3. So when I look at this, I see, okay, well, the lever arm in this case is still this red lever arm that we drew for F2, because we're going from the pivot all the way over to the point where the force is applied, and F3 is applied at the end of the door. However, there's no perpendicular component to the lever arm for F3. It's completely lined up with it. So you can think about that either as the angle is 180 in this case, and sine of 180 is 0, or you can just say there's no perpendicular force, so it's not going to exert any torque. So the torque from F3 is 0. When a block of mass M is hung from the bottom end of a vertical cylindrical rod, the rod stretches a distance d. If the same block is hung from another rod made of the same material, but with twice the length and twice the radius, by how much will the rod stretch? So in this case, we're looking at how much some solid object with certain dimensions stretches. So we want to be thinking stress and strain and Young's modulus. So we know that the amount that a rod stretches is the force applied times the initial length divided by the area and the Young's modulus. So with these questions, I always draw a picture. So we start out with a rod, and we're hanging a mass M, and this has radius R and length L. Now our new rod has twice the length, but it actually has twice the radius too, so I should really make it a little bit thicker there. So its length is 2L, and its radius is 2 times the old radius when we hang a mass, and we want to know how much does it stretch in terms of the old stretch. So I'm going to apply this equation in both situations. So if this is the old situation and this is the new situation, we can say, okay, the delta L old is equal to the force applied, which is just mg in both cases, so that's the same, times its length, so here the length is L, and then we divide by the cross-sectional area A, which is pi r squared, times the Young's modulus. In the new case, delta L new is equal to the force applied, which is mg, so it's the same F as we have over here, times its L, divided by pi r squared y. So now let's substitute in 2L and this 2R over here. So we have F times 2L divided by pi 2 little r squared times y. And if we work this out, so one of the factors of 2 will cancel, so we'll get FL over 2 pi r squared y. So this is equal to 1/2 FL over pi r squared y. And notice that this is our L old. So that means that our delta L new is equal to half of delta L old. So that says that delta L new is shorter than delta L old by a factor of 2. So the rod will stretch a distance half d. Standing rigidly with your arms by your sides and your feet planted to the floor, you begin to fall backwards. How fast is your head moving right before it hits the ground? You may approximate your body as a uniform rigid rod of length L, and the moment of inertia for a rod rotating about one end is ml squared over 3. Then, once you've found an algebraic expression, please estimate a numerical answer. Okay, so when I look at this problem, I can think of two ways to solve it. I could use forces and torques, or I could use energy. And I know that there's no time here, which is a hint that energy is probably the way to go. So I noticed that there's no non-conservative forces at work here. There's no friction or anything. So energy conservation is probably a good choice. Because there's no non-conservative forces, we can conserve mechanical energy, so that means that the initial kinetic energy plus the initial potential energy should be equal to the final kinetic energy plus the final potential energy. So the initial state is when the person is upright. So in this case, the person is falling from rest. So the initial kinetic energy is 0 because nothing is moving. So that will give us 0. What's the initial potential energy? So the force that's creating the potential energy is gravity. So the gravity acts at the center of mass of the person. So it's going to act at L over 2 because we can approximate our body as a uniform rigid rod of length L. So that means the initial potential energy should be mgh, where h is L over 2. So in the final state, the person is flat, but moving. So in that case, everything is at h equals 0, so there's no potential energy, and all the energy is kinetic. So this is a thing that's rotating. So we can use rotational kinetic energy here, which is 1/2 I omega squared. So we were told the value for I, so mg L over 2 equals 1/2 I is ml squared over 3 times omega squared. Now we want to know the speed of the head right before it hits the ground. So we're looking for a speed. And we know that speed is r times omega. In this case, r is L. So if we want the speed of the head, we take the angular speed and multiply it by the distance between the pivot and the head, which is L. So this tells us that omega is v over L. So I can take that and plug it in here, and I get mg L over 2 equals 1/2 m L squared over 3 times v squared over L squared. So now we can cancel quite a lot of things. So these L squareds cancel, the m's cancel, these 2's cancel. So we're left with GL equals v squared over 3. So if we solve that for v, we get square root of 3GL. So now to estimate that speed, we say, okay, well, a person is on the order of, I don't know, 2 meters. That's a very tall person. Maybe we should go like more like 1.5 meters, something like that. So v is equal to the square root of 3. G is approximately 10 meters per second squared. We're just estimating, so let's just use that. And then we'll multiply that by 1.5 meters. So that gives us 30 times 1.5, which is about equal to square root of 45 meters per second squared. And the square root of 45 is approximately equal to 6 point something. maybe, I don't know, let's call it 6.5. I don't know exactly what it is, but we're estimating, so it doesn't matter that much. So that's about 6.5 meters per second. A block of wood with density rho B equals 900 kilograms per cubic meter is initially floating at the surface of water shown in the figure. At equilibrium, what percentage of the volume of the block lies below the water level? Okay, so if we want to figure out percentage of volume below water, that's going to be the volume submerged divided by the total volume of the block. So we need to see if we can figure that out. So I'm going to start by drawing a free body diagram, because this seems like something that's going to involve buoyancy, since we've got a block floating in water. So if we draw a free body diagram for this block, we're going to have force of gravity pulling down. So this is going to be the mass of the block times g. And we have a buoyant force upwards. And that buoyant force is going to be equal to the weight of the water displaced. And the water displaced is equal to the volume of the block that's submerged. So let's write this down. So this block is at rest. So we know that these two forces are equal and opposite. So F buoyant equals Fg. So the buoyant force is the mass of the water displaced times g, and Fg is mvg. So we can cancel the g's and then rewrite these masses in terms of their volumes and densities. So the mass of the water is going to be the density of water times the volume. Now what volume is it? You have to be careful. So it's the volume of the water displaced, so it's this submerged volume. And that has to be equal to the mass of the block, which is going to be equal to the density of the block times the volume of the whole block. So this is great because we have V sub and V block, and we need that ratio. So I'm going to move V block over here. And the other side will then be rho block over rho H2O. And we know the density of the block is 900 kilograms per cubic meter, and the density of water is 1,000 kilograms per cubic meter, and that gives us 0.9, which is 90%. So 90% of the block is underwater at this point, so it's like most of it, so it's really probably down like that. Okay, so for the second part, you now pour oil, which has a density of 800 kilograms per cubic meter, on top of the water. And when the system comes to new equilibrium, what percentage of the block's volume lies below the water level? So in this case, we're still looking for V submerged in the water divided by the volume of the block. So let's again draw a free body diagram. So in this case, the block is sitting both in water and in oil. So there's two buoyant forces. So we have Fg pulling down, just like we did before. We have the buoyant force due to the water, and we have a buoyant force due to the oil. So the block is at rest, so the sum of the forces is 0, which means that F buoyant water plus F buoyant oil has to be equal to Fg. So F buoyant water. F buoyant water is going to be equal to the mass of the water displaced times g, and F buoyant oil is going to be the mass of the oil displaced times g. I'll put a little displaced here just so we remember. And that's going to be equal to the mass of the block times g. So all of these G's cancel, and the mass of the block is still the density of the block times the volume of the whole block. The mass of the water displaced is going to be equal to the volume inside the water. So this is the volume of the water displaced times the density of water. And then the oil, it's going to be this volume, so the volume of oil that's been displaced times the density of oil. So we don't know what these two things are, but we do know that if we sum the volume of the oil displaced and the volume of the water displaced, we should get the volume of the whole block. So VH2O displaced plus V oil displaced has to be equal to V block. So now we have these two equations and these two unknowns, and what we want to get is V submerged, so that's the V water displaced divided by V block. So we want to get rid of the volume of the oil displaced. So if we solve for that over here, V oil displaced is V block minus V H2O displaced. So we can take this and plug it in here. And then we have enough information to solve for V water displaced over V block. So I'm going to abbreviate this as VH2O, rho H2O, plus V block. Actually, I'll distribute this oil, plus V block rho oil minus VH2O rho oil equals rho block V block. Now over here we can simplify this a little bit. We can say VH2O is rho H2O minus rho oil plus V block rho oil equals rho B V block. And then I can move this term over to the other side and factor that out. So this side on the right will become V block times rho block minus rho oil. And on this side we have V water rho H2O minus rho oil. So now if we solve for the ratio VH2O over V block, which is what we're after, that's going to be rho block minus rho oil over rho H2O minus rho oil. And rho block was 900 kilograms per cubic meter. Rho oil is 800. And in the denominator we have rho water is 1,000. Subtract off rho oil again. So this gives us 100 over 200, which is 50%. So that means that when you pour oil on top of the water, the block actually lifts out of the water higher than it was in part A. A physical therapist is testing the strength of a patient's biceps. She has the patient hold a ball of mass M with radius 10 centimeters in his hand. She increases the mass of the ball until the patient can just barely hold his arm at an angle of 105 degrees, which occurs when this mass over here is 35 kilograms. The center of mass of the patient's arm is located 15 centimeters from the elbow, and the arm has a mass of 2 kilograms. The patient's biceps connect to the arm 5 centimeters from the elbow joint. What is the magnitude of the maximum force the biceps can withstand F biceps? So that was a lot of information. The first thing I would do is draw a simpler picture, because this is quite busy over here. So let's draw the arm. So we're looking at the arm, and we're treating it as a stick. So let's draw a horizontal stick here. All right, now let's look at our forces. So what forces are acting? So this is the joint, and 5 centimeters away from the joint, we have the bicep force. So the bicep force is going off in this direction, F bicep. And this distance here is 5 centimeters. And this angle is 105 degrees. Okay, so that takes care of the bicep force. The joint here is also exerting some force, but we don't know what it is. I'm just going to put F question mark there. Then 15 centimeters from the joint, we have the center of mass, or the mass of the arm. Let's draw that in. So that's going straight down. So this is FG arm. And then out here at the end of the arm, 35 centimeters away, so I guess we should denote this. This distance is 35 centimeters. And this whole distance from here all the way to the end, where the ball is 35, oh, whoops, this is 15. 15. Okay, so that final force, the ball is going to exert a downward normal force on the hand, and because nothing is moving, we know that that's just equal to Fg, which is equal to mg. Okay, so I think we've got all the forces now. So this arm is in static equilibrium. So we know that the torque around any point has to sum to 0. But I don't know what this force is here, so I'm going to choose to put my pivot right here. So now I'm going to sum the torques around that pivot. So the sum, let's make that a little bigger. The sum of the torque is equal to 0. So 0 equals, so now we need to figure out the torque from each force. So let's start with FG arm. So we know that torque is R cross F, or the magnitude of the torque is R F perpendicular, or R perpendicular F. So here, so FG arm and FG from the ball are both completely perpendicular to the lever arm. So the torque from FG arm will be the distance, which is 15 centimeters, times this force, which is the mass of the arm, times G. And this torque is going to rotate clockwise, so this is a negative torque. For the force from the ball, that's also a negative torque. It's at a distance of 35 centimeters, and we multiply by mg in that case. And now we need to take care of the force from the bicep. So that is a counterclockwise force, so it's positive. And this has an angle, so we have to figure out the perpendicular component of F bicep, because that's the only part that's going to come into our equation here. So the distance is 5 centimeters, and now we need F perpendicular from the bicep. And now what is that? So this is 105 degrees. So if we take the sine of 105 degrees, that should give us the perpendicular component. So I'd rather think about this in terms of angles less than less than 90 degrees. So what would I like to do here? So if this is 105 degrees, then this angle is 180 minus 105, which is equal to 75 degrees. So I'm going to say, okay, this is equal to F bicep times the sine of 75 degrees. Okay, so all these centimeter units cancel, and we can now solve for F bicep. So F bicep is equal to 1 over 5 centimeters times the sine of 75 times 15 m arm g plus 35 mg. And if we work that out with the numbers, we should get about 25,000 newtons. For the next part, the therapist has the patient perform the same test while his arm and the mass are fully submerged in a swimming pool. Given your answer from part A, so we figured out the maximum force that the person can exert with their bicep, what is the maximum mass M the patient can now hold in place? And it tells us we can model the arm as a cylinder of length 30 centimeters and radius 4 centimeters, and the mass has a constant volume with radius 10 centimeters. Assume that the buoyant force on a submerged object acts at its center of mass, and recall that water has a density of 1,000 kilograms per cubic meter. Okay, so how is this case going to be different than our old case here? So I think I'm going to take this and copy it. Paste it here. So let me get rid of some of the extraneous stuff. Okay, so we had our force that we don't know from the joint, the force of the bicep, the gravitational force on the arm, and the ball. We still have all of those forces, but now we have a couple extra forces. So because the ball is underwater, there's now a buoyant force that acts upward on the ball. And there's also a buoyant force that acts upward on the arm. And we were told to assume that that acts at the center of mass of the object, which is right here. So this is the buoyant force on the arm. So again, I'm going to choose this point to be my pivot because I don't know what that is. We now know what the bicep force is. So we know the bicep force, we know this, we know this. So we're going to just sum the torques again and set it equal to 0. So in this case, we're going to have the same thing we had before. So 0 equals, so we need the torque from the bicep, which is the force from the bicep, times the distance, which was 5 centimeters, times the sine of 75 degrees. That's a positive torque. Then we're going to subtract off the gravitational force torque, which acts at 15 centimeters. It's perpendicular, so there's no sine or anything. So That's just FG arm, which is M arm times G. But now there's also a buoyant force that acts in the positive direction. So we have to add 15 centimeters there times the buoyant force, which is the mass of the H2O displaced by the arm, times G. Then we've got to do these two forces. So this one is still a negative torque, so it's negative x at 35 centimeters. It's perpendicular, so there's no components to take, so it's just 35 times mg. And now we have to add on the buoyant force associated with the ball, which is going to be the 35 centimeters. It acts at 35 centimeters, perpendicular, no components. And we need to find the buoyant force from the ball, which is going to be the mass displaced of water displaced by the ball times G. Okay, so now we have to do a mess of algebra. So what are we looking for? We're looking for what's the maximum mass m the patient can now hold in place. So we're looking for this m. And we have to figure out a few things. So we know the mass, we know the bicep force, we know the arm mass. What's the mass? The mass of the water displaced by the arm. So that's going to be equal to the volume of the arm times the density of water. And the arm is a cylinder. The arm is a cylinder that has a length of 30 centimeters and it has a radius of 4 centimeters. So the volume of this is pi r squared times the length L. So this will be pi r arm squared times L times rho H2O. Okay, we know we're looking for this. Now we need to figure out what this is. So the mass of the water displaced by the ball is going to be the density of water times the volume of the ball, which will be rho water times the volume of the ball is 4/3 pi times the radius of the ball cubed. So if now we can solve for m, and if we plug in all of these numbers, we're going to get that the biggest mass that the person can hold is 40 kilograms. A 25 kilogram child is riding in a bumper car of mass 300 kilograms at the amusement park. The child drives straight into a wall. The walls of the bumper car ride are lined with spring-loaded guardrails, so each one has an effective spring constant of K effective equals 520 kilonewtons per meter, which means that the cars will bounce back. Assume that the car and the child have a speed of 4 meters per second just before crashing into the wall, and the same speed after the collision in the other direction. For how long was the car in contact with the wall? You may treat this part of the motion as simple harmonic motion. Okay, so what we have here is a mass. It's moving along and it comes into contact with a spring. So what happens at that point? So the mass goes to the right, it comes into contact with the spring, it will compress the spring, the mass will come to a rest, it'll turn around and go back the other way. And when it passes back through this point, the mass will become detached from the spring because it's not glued onto it. If the mass was glued to the spring, then it would come in, it would compress the spring, it would come back, then it would extend, and because it stuck to it, the mass would stop again, and the spring would turn around and bring it back. And that would be one period of this mass M glued to this spring with spring constant K. So that period of this whole cycle would be 2 pi times the square root of the mass divided by the spring constant. But in this case, it's not in contact for this whole oscillation because there's no glue. So the only part of the cycle that is relevant is this part right here, which is half of the total period. So the time, let's call it the time delta t, that our mass is in contact with the spring is 1/2 of the period. And if we plug that in, we just get pi times the square root of m over k. And if we plug in all of the relevant numbers, that's about 0.079 seconds. A mass m is placed on a spring with spring constant k on a horizontal surface with friction, as shown. Let x equals 0 be the equilibrium position of the mass. The spring is then compressed a distance d and released. It travels to the right, detaching from the spring as it passes x equals 0, and finally comes to rest somewhere over here, a distance L from x equals 0. Determine the coefficient of kinetic friction UK between the mass and the floor in terms of mkd, L, and G. Okay, so when I look at this, I see, okay, the mass is feeling some forces. It's feeling the force from the spring. It's feeling the force from friction. There's gravity, there's the normal force. I could work out, it seems like maybe I could use forces to solve it, but I noticed that this question doesn't mention time, which usually hints that the problem is easier to solve using energy considerations. So let's think about how we can do that. So when I look at this, I look at the initial state. So here's the initial state of the system. And I think, what's the energy, the total energy of that initial state? So in this case, it was compressed to distance d and the mass isn't moving. So there's no kinetic energy. No heat has been generated. So there's no internal energy that we need to consider. But there is spring potential energy. So the initial total energy of this system is just the potential spring energy, which is 1/2 k d squared. Okay, so now I'm going to look at the energy of the final state. So in the final state, the mass here is at rest, so there's no kinetic energy. There's also no potential energy because the mass's height hasn't changed, and the spring is no longer compressed with the mass on it. So where did the energy go? Well, because there was friction, the floor has gotten hotter, and the bottom of the box has gotten hotter because of the friction force. So the energy was converted from mechanical energy to internal energy by the friction force. So this has got to be the work that the friction force did is the only energy left in the system. So the final energy is all heat, and it's equal to the work done by friction, or the magnitude of the work done by friction, which is mu times the normal force, that's the force of friction, times the displacement. So how far it went, because that's F dot dr. That's the work done. So what is this? So it's mu times the normal force. There's nothing sitting on the block. So the normal force in this case is mg. And how far did it go? Well, the block started here at minus d, and it stopped at plus L. So the total displacement is d plus L. Energy is conserved, so I treated the whole system, including the floor, as my system. So I lost no energy, it just turned into heat mediated by friction. So I can say that my initial energy is equal to my final energy. So we have 1/2 k d squared is equal to mu mg d plus L. And we're solving for mu. We want to find mu. So we just divide both sides by mg d plus L. So we have k d squared over 2mg d plus L. And that is our coefficient mu.